Hi, in this video we will talk about the sequence and we will see some of the examples of the sequence and the problems related to that sequence. And the second is that we will talk about the arithmetic sequence and we will see what actually is arithmetic sequence and what is a general term for the arithmetic sequence, and we will do some of the problems related to this arithmetic sequence. And someone say this is an AP, that is also known as to be a arithmetic progression. So we will talk about them. So first of all, we talk about the sequence. So sequence is a special kind of function that has a domain to be a natural number. So that is whose domain, this is a domain of this function. And here what does mean by this natural number? Then usually you have seen that from the natural number we can think of to start from 1, 2, 3 and so on. But here we are taking it to starts from 0, which is usually known to be whole numbers, but we take this notation, and that is a standard notation in the advanced mathematics, that a natural number that starts from 0, 1, 2, 3 and so on, and mm, n positive, that is positive natural number, that denotes the numbers that starts from 1. So 1, 2, 3 and so on. So uh, we use these notation, and here this domain is natural numbers. So sequence is usually denoted by an. Here an is nth term of this sequence, and that n starts from 0, 1, 2 and so on. And otherwise it will be stated if we are taking n to be a different one, like if we are taking n to be from 1, then it will be stated here. So here we take the few of the examples. We look, let's say we have 2, 4, 6, 8 and so on. So you can see that here the first term is 2, that is a1, and the second term is 4, which is a2, third term is 6, which is a3, fourth term is 8, which is a4. And can then what will be an? So can you tell me that what will be the formula for n? So here the formula for an will be 2n, where n starts from, obviously, from greater or equal 1, or someone write this like n belongs to, in our notation, that is n positive. Okay, so now we look at other example, and this is uh, the first term is 1, and second term is -1, and third term is 1, again -1 and so on. So you can see that here the first term is a1, is 1. The second term is a2 to be equals to -1. Third term a3 is again 1. So we can say from here that even terms are -1 and odd terms are 1. So what will be the general formula for an? So someone can write this to be like 1 and -1, and can write n is odd, n is a1. So is there any other way to write this general formula? So can you think of that? So I can write this an equals to minus 1, and that makes it, let's say we put here that, actually what actually we are having that, when n is odd, that must gives 1, and n is even, that gives minus 1. So what could be here to make it this? So there is n plus 1, which makes when we put n equals to 1, then it will makes 1 plus 1 to be 2, then minus 1 raised to power 2 is 1. And when we plug any of the odd numbers, then that will makes it positive, even, and that will makes it positive 1. And when we plug n to be even, then that will makes it negative. So the general formula for the above sequence is this one, right? So we look more example to find the general term, and we look, and the here the question is, does every sequence can be written in the formula like that just by plugging n, we can get the an? So to answer this question, that every can we have every sequence to write as a formula like this, that just by plugging in we get any of the term? So we look the example here. So here we have a sequence that is written by 1, 3, 6, 10, 15, and 21. And you can see that A1 is here 1, and A2 is 3, A3 is what? This is a 6, and A4 is 10, A5 is 15, and A6 is 21. Then how we can get the general formula, or really we can have a general formula for this? So first of all, we recognize what actually is the pattern here. So you can see that by adding here plus 2, we get the next term, and by adding plus 3 in this term, we get the third term, and similarly plus 4 by adding into this, we get 10, and plus 5 we get 15, plus 6 we get 21. So from here I can see that this is nothing but a1 is 1, and a2 is a1 plus 2, a3 is what? This is a2 plus 3, and a4 is what? A3 plus 4, a5 is a4 plus 5, and a6 is a5 plus 6. So just from here we can see that what would be an? So an will be equals to an minus 1 plus n, right? But that depends on the previous term, n minus 1 term. So this is not like a formula that just by plugging n we can get a like a 100 term, because to get a 100 term we need to find a 99, and to find a 99 we need a 98 and 97 and so on. All terms must be known. So this is known as the recursive way to define a sequence. Okay, so for that we can have a general formula like that only depends on n, and we cannot have as well. So in general the answer for the previous question is no, that we can't have a general formula for each sequence. So another example for a sequence that is defined recursively is this, that is an equals to an minus 1 plus an minus 2, where a0 equals to 0 and a1 equals to 1. So you can see that this is a sequence that depends on the two values defined before, that is n minus 1 term and n minus 2 term. So this is sequence. If we look the terms of this sequence, then a2 will be equals to what? And just by plugging n equals to 2, we get a1 plus a0. So we are known. So we get this 1, and similarly a3 will be equals to a2 plus a1, which will makes it 2, and a4, which will makes a3 plus a2, which will make 2 plus a3 is 2 and a1 is 1, so which will make it 3. And this sequence has a particular name, and that name of this sequence is Fibonacci sequence. And it has a very much beautiful application in the nature, and we will discuss in the next video, some next video. But this is a sequence that depends on the two different values previously defined. Now we look at another example. So in this example, a n is given, which is n over n plus 1, and he asked to find a20 and a21. Then how we can find this a20 and a21? That just simply plugging n equals to 20 and n equals to 21. So we get a20 equals to 20 over 21, and a21 to be equals to 21 over 22. And another example is like this is a n equals to n plus 1, a n minus 1, where a1 is equals to 1, and he needs to we need to find a5. So look, to find a5, if we plug a5 n equals to 5 into this formula that is given recursively, we get what? We get a5 to be equals to 6a4. So but we don't know what is a4. So to find a4, we need to find we need to plug n equals to 4 into this formula, and then still we need to find a3 and so on. So we have to find all ai's from 1 to 4 to get a5. So we compute them, first of all a2, and then a3 and a4, and then we will be able to get a5. So a2 will be equals to 2a1, which makes it 2. a3 will be equals to 3a2, which will makes it 6. And a4 will be equals to uh, can you see that that must be a 3 here. So that 3a1 must be exit 3, because n plus 1, and then we are putting n equals to 2, so 2 plus 1 equals to 3. So here will be equals to 4a2, and which will makes it what? That will makes it 12. And here 5a3, which will makes it 5 times 12, so which will makes it 60. So now we have known we are known to find we are known about the a4. So a5 will makes it what? That will makes it 6 times a4, which is 60. So which will makes it 360. So a5 is 360 here, right? So you can see here that for the recursively defined sequence, the problem is that if we need to find the 8000, then we have to find also 999 all the terms before that. So that makes a complicated computation. So we actually are hopeful to find for the general term, but this is unfortunate is not true for each sequence. But the most interesting that if we are known to a general formula, then that is easy to compute the any of the term. But if we are define the n term recursively, then it will makes a complication, and it makes a more working thing to find any of the particular chunk. So here is the problem, that we need to find the next two terms of each of the following given sequences, and also we need to find the an, but maybe that will be a closed or either by a recursively defined. Okay, so the first one is that uh, given here, that is 2, 6, 11, 17, and so on. So first of all, we look what actually is the pattern here. Then you see that here a1 is what, this is 2, and a2 is 6, a3 is 11, and a4 is 17. And you can look the pattern, that how we obtain a2 from a1, and a3 from a2, and a4 from a3. So simply just taking here plus 4, then plus 5, then plus 6. So from here, I can ask you what will be the a5 that we need to find. Simply it will be adding 7 into a4, that will make it 17 plus 7, which is 24. And a4 6 will be equals to what, we need to add what, that we have added 7 into a5, then we have to add 8 into a6, then that will make 24 plus 8, which will make it 32. Now I can ask you, what is an? So you can see that this is actually a1, and this is actually a2 plus 4, which can be written as a2 plus 2 plus 2. Okay, and a3 is what, that is a2 plus 5, which is actually written to be a2 plus 3 plus 2, that is 30, and then we add a 2. And similarly, a4 is what, that is a3 plus 6, which is a3 plus 4 plus 2. So from here, what will be an? Can you realize what is an? Simply that will be, an will be equals to an minus 1 plus n, that is n, that is nth term, and by adding 2 into it, so by adding this n plus 2 into an minus 1, we get an. Okay, so you can check it, like if we want to find a3, so it will be equals to what, n equals to 3, we get a2 plus 3 plus 2 is 5, which is true. Okay, so this is the an formula that is defined recursively. So second question is given in that, which is uh, 1, 3, 12, 60, and so on. So that first term is a1 equals to 1, a2 equals to 3, a3 equals to 12, and a4 equals to 60. So we look the pattern, how we get a2 from a1, and a3 from a2, and a4 from a3. So you can see that here, that a2 is obtained by multiplying 3, right, and a3 is obtained multiplying 4 to a2, and similarly multiplying by 5 to a3. So what will be a5? So a5 will be equals to a4 multiplied by 6, so which makes it 60 times 6, which is 360. And what about a6? So in the same pattern following, we get a6 to be equals to 360 times 7, which makes it 2520. So from here, can you write the an? Yes, we can write this, that an is what, that is an minus 1, and multiplying what, multiplying. And here you can see that when we are having a2, we multiplying by 3, which is n plus 1, and when we are having have a3, we are multiplying by 4, previous term, so which is actually again n plus 1, so that is n plus 1. So simply, so you can check it, that if we plug n equals to 6, then what will be that? That will be a5 multiplied by 6 plus 1, which is 7. So that is here. That was a5, and that is a 7, which is actually n plus 1. So this is the nth term for this example. So to the next one, that is a third part into the given problem, which was 7, 9, 12, and 16. So you can see here that a1 is 7, and a2 is what, that is 9, and a3 is what, that is a3 is here 12, and a4 is 16. And we look the pattern, what actually the pattern is, that here that we, by adding 2 we get 9, and by adding 3 we get 12, by adding 4 we get 16, and here a1 is 7. So what will be a5? So a5 we get what, by adding 5 into the previous one, which will make this 21, and a6 will be obtained by adding 6 in the previous one, which will make it 27. So we can think of an. So an actually, we are adding n into the previous one, that is an minus 1 plus n, but a1 is given, which is what, that is 7. So this sequence can be represented by this formula with this initial term, which is a1 equals to 7. Okay, so now we go move to the fourth one problem, which says that we have 1, 3, 7, 15, and 31. And so are you a bit worried about it, that it makes difficult? No, this is not, but just we have to be focused about what actually is happening here. So first of all, we write it like terms we write that are given, and now we look the pattern what actually is happening. So here, that is how we are obtaining, that is by adding 2 into a 1, we are getting 3. So by adding plus 4, we are getting 7. By adding plus 8, we are getting 15, and by adding 16 into it, we are getting 31. So what is actually 2 is, that is 2 raised to power 1, and 4 is what, that is 2 raised to power 2, and this is 2 raised to power 3, this is 2 raised to power 4. So what will be a 6? So we are adding that one increasing power of 2 by n minus 1. So a 31, that will be 31 plus what? That will be 2 raised to power 5. So which will make it 31 plus 32 is 63. Is it? Is it easy? Yeah, this is easy, but just we need to look what actually is happening very carefully. So here a7 we can obtain by just a6 plus 2 raised to power 6. So what is this? This is x, a6 is, we have 63, and 2 raised to power 6 will be what? That will be 64, which will make it 7 and 127. Okay, now now the question for an, what is an in this sequence? For this sequence, what will be an here? So you can see that an is actually an minus 1, that is a previous term, by adding 2 raised to power what? Look here, that a2, and we are adding power 1, so which is n minus 1, and a3 we are adding power 2 raised to power 2, which is again n minus 1. So here that will be n minus 1, with a1 is what? A1 is 1. So this is a recursive definition of this given sequence. Okay, so we are done with this examples. Now we talk about a special type of sequence that is known as the arithmetic sequence. Someone say this is an arithmetic progression as well. That sequence also can be known as to be a progression. So that is denoted by AP as well. So what actually is arithmetic sequence? So in arithmetic sequence, each term is obtained by adding a constant in the previous one. In other words, we can think of it like the difference between consecutive terms is constant. That is, if we have nth term, then an minus 1 term will be equals to d. That d is a constant which is known to be a common difference. So by taking this into our mind, we get what is the general formula for this sequence. Okay, so general term will be like if we have a1 is a1 and a2 is what? That will be a1 plus some adding a number, that is a d, and a3 will be what? That will be a2 plus d, right? Then a1, by putting this a1 plus d, by because a2 is a1 plus d, then by plugging this we get what? We get a1 plus 2d. Similarly, a4 will be equals to a3 plus d, which will make it a1 plus 3d. So from here we can see that the nth term an will be what? That will be equals to a1 plus n minus 1 into d. Here d is already, we know this is known to be a common difference, and that is n is telling about the number of terms, right? Number of terms, and this an is denoting the nth term. So from this general formula we can see that if we know, because there are four unknown, that is a first term. So if we know the three of them, then we can find the fourth one easily, that we will see into the next examples. So here in this problem, he says that if the fifth term of an AP is 13 and 17th term of an AP is 49, so we need to find AN and A13. Okay, so as given is A5. So A5 is given, which is 13, and A17 is given, which is 49. So what we need to find? We need to find AN. So this AN is of a AP, so that will be equals to A1 plus n minus 1 into D. So definitely to find a1 an, we need a1 and d. So to find them, we are given these two conditions, that is the fifth term is 13 and 17th term is 49. So by general formula we can write that a5 can be written as a1 plus 4d, because this is an AP, so that will be equals to 13. And similarly a17 will be a1 plus 16d, which will makes it 49. And this is our in very much interesting system of linear equation to find the solution for a1 and d. So first of all we subtract first equation from the second one, and we get what? That we get 12d equals to 36. Okay, so d will be equals to what? That is a 3. So as we know now d is 3, so we need to find a1. So we plugging in any d in any of the equation, we can find a1. So if I plug this d to into the first equation in this one, we get what? That will be a1 plus 4 into 3 equals to 31 13. So a1 will be equals to 1. Right now d we know, a1 we know, so what we need to find? We need to find an. So an will be equals to what? Just plugging in these values, that will be 1 plus n minus 1 into 3, right? So that will makes it 3n minus 3 plus 1 is minus 2. So an is 3n minus 2. So now we have to find a13. So simply plugging this n to be equals to 13 into this formula, we get a13, which will make it a13 equals to 39 minus 2, which is equals to 37. Okay, so we were given that fifth term and 17th term of an AP, and he has asked us to find the AN. So we need to find A1 and D to find AN. So we use these given condition, and we get A1 and D, and by plugging we get AN. This is a general formula for AN we have obtained. Now just by plugging n equals to 13, we get the answer for A13. Okay. So here we have another example that says that find the number of terms in AP if the first term is 3, AN is 59 and D is 9. So this is an other example for the application of the general formula, that we have AN to be equals to A1 plus n minus 1 into D. Then we need to find the n, right? So here we are given all other values, and we can find n just directly plugging the values and doing some algebraic manipulations. So here that by putting a 59, and here a1 is a 3 and we have to find, and d is a 9. So you can see that is a 59 equals to 3 plus 9 n minus 9. So that will makes 59 equals to 9 and plus minus 6. Okay, so we get what? 59 plus 6, which will makes it 9n, and this is what? This is 72. Okay, can we add them? 9 plus 6 is 5. Okay, sorry, this is 5, so this is a 65, which is equals to 9n. So just dividing by 9 on both sides, we get n. So what we get? So we get 65 over 9, which is actually is not a real number, because if that will be a 7 9 the 63, so it makes things that the given information for the sequence is not correct, because that must give a natural number. So if I change the problem, like if I take d to be equals to 7, then what we see what happened. Okay, because that is not a natural number which is not correct, so it means that the given information is not correct. Okay, so we change it that d to be equals to 7, then that will makes it 59 equals to 3 plus n minus 1 into 7. So that makes it 59 equals to 3 plus 7 n minus 7. So that will makes it 59, and here that will be negative 4, that will comes here to make it plus 4, which makes it 7n. So 59 plus 4 is 63, is 7n. So now you can see that that gives a natural number which says that n equals to 9 sevens are 63. So n, the ninth term of this sequence is 59 if d is a 7. So from here you can also conclude that if we change the d, that in this given set of information, so maybe that makes it not an ap. Okay, because that nth term we are fixing here, so that makes things like that. Okay, thank you.